Hello, I'm Wallace Lira and I will present GANHopper, a top game for unsupervised image-to-image translation. How would a dog look like as a cat? Our general-purpose image-to-image translation network aims to solve problems like this. Difficult tasks, such as transforming image contents with significant changes, are best accomplished one small step at a time, as shown in this video. Even though many of the individual changes are minimal, the final result of the editing process is considerably different from the original image. We now present a brief overview of the literature. There are two main philosophies for direct image-to-image translation. Some methods operate on the shared latent space assumption, while others operate on the cycle consistency assumption. The shared latent space assumption implies that there exists a shared, low-dimensional latent space between the source and target domains. Some of these works have been very successful, with Unit in special inspiring many follow-up works. This approach can also be extended to enable multimodal translation as done in MUnit. This is achieved by separating the latent space for content and style. That way, any translation has its content retained while the style changes. The seminal works for using the cycle consistency assumption in image-to-image translation were Dual GAN and Cycle GAN, both simultaneously proposed at ECCV 2017. The premise of this assumption is that by translating one image to another domain and back, this reconstruction needs to be close to the original image. Many works exploring the cycle consistency assumption aim to propose architectural improvements and creating more refined losses, such as GANHopper by Kokaslan and others. For instance, one of the key contributions of this work is proposing the use of dilated convolutions on the discriminator. In fact, the shared latent space assumption implies in the cycle consistency assumption, but not vice versa, according to the authors of Unit, Liu and others. Our work operates on the cycle consistency assumption, but it performs small discrete changes in succession, which we call hops, instead of trying to perform all the changes in a single operation. It is not a recurrent cycle GAN and does not increase the network capacity compared to cycle GAN. We will now present the details on how our network is trained to perform such translations. The loss function is a weighted combination of a cycle consistency loss, an adversarial loss, a hybrid domain loss, and a smoothness loss. Rather than enforcing cycle consistency between input and output images, as in CycleGAN, we enforce it locally along every hop in our multi-hop translation. The orange arrows represent the cycle consistency loss performed for each individual hop, which are all summed up to represent our multi-hop cycle consistency loss. This is how we state the cycle consistency loss. The adversarial loss is enforced as normal for each forward hop, taking into account the target domain only. The adversarial loss is represented as follows. Each generated image has its domain ambiguity evaluated by a binary domain classifier network, D8, whose architecture is the same as CycleGAN's adversarial discriminator. In other words, D8 is trained to output 0 for ground truth images in domain X and 1 for ground truth images in domain Y. During the training of the generator, D8 showed a daily output 0.25 for the image produced by the first hop and output progressively higher values until achieving 1 in the last hop. This is how we state the hybrid loss. The smoothness term penalizes the image space difference between each subsequent hops, as represented by the green arrows. This term encourages the hops to be individually as small as possible, while still leading to the full translation when combined. This has a regularizing effect on the training. This is how we state this loss. For each image to be translated, we perform a single hop and update the weights of the generator and discriminator networks. Then, we perform the next hop in a similar fashion. Training this network this way rather than performing all hops and then doing a single weight update has the advantage of requiring significantly less memory. Using one specialized generator for each specific hop would also considerably increase memory usage, scaling linearly on the amount of hops. The results reported in this presentation use these three datasets for dog, cat, and human faces. Here we present first some qualitative results of our approach for cat-to-dog translations. Our full translated results tend to retain salient features while still preserving input features when compared to the other approaches. Note, in special, how the four patterns tend to be preserved. We also observe that, in some instances, performing more hops can help improving the image. Notice how these dogs' features get sharper, for instance. The same phenomena can be seen in other examples to some extent. We also evaluate how the percentage of pixels translated varies as a function of the number of hops performed, using DeepLab v3. While not strictly linearly translating the pixels, it is still a smooth monotonic function, suggesting that the hops successfully encourage in-between images that can be interpreted as domain hybrids. We can observe the same phenomena when translating from cats to dogs. Here, we present a quantitative comparison between different methods for dog-to-cat translations. The horizontal axis presents the average perceptual similarity between all inputs and their respective outputs. The vertical axis presents the percentage of output pixels correctly labeled as the output class by a pre-trained network. Higher and to the right is better. And here are the quantitative results for the cat-to-dog translation. We can see that CycleGAN produces outputs that best resemble the input for both directions, but fails to perform domain translation. Our approach performs unit, GANHopper, and DiscoGAN in both metrics. This result indicates that one does not necessarily need to sacrifice domain translation ability to preserve salient features of the input. We also perform a qualitative analysis of cat-to-dog and dog-to-cat translations using Amazon Mechanical Turk to evaluate how real the generated images are perceived to be, and the extent to which GANHopper and the other image-to-image translation baselines succeed at the translation task. The results indicate that our method was outperformed exclusively by GANHopper how real the generated dogs are perceived to be. However, GANHopper outperforms GANHopper if one also takes into account the translation task, measure in which the later network had the worst performance compared to the other approaches. We also performed an ablation study to explore the impact of the two proposed losses. The results of using the recommended parameters are in the second column. By setting the weight of the smoothness loss to 0, the network suffers from mode collapse, as seen here. Using an intermediary value for this weight does not yield better results. Similarly, we can observe why setting the weight of the hybrid loss to 0 tends to produce slightly less sharp features. On the other hand, increasing the weight of the hybrid loss any further yields more artifacts in the translation process, as can be clearly seen in the eyes of the generated cats, for instance. GANHopper is a general-purpose network. As such, we performed experiments with other datasets as well. For instance, here are our results for human-to-cat translation. And here are the translation results for the other way around. Notice how fur color successfully translates into hair color, and how head poses are preserved during the translation process. In our work, we use the cycle consistency assumption while introducing the multi-hop paradigm to exert fine-grained control over the translation using a new hybrid discriminator. We also introduced two new losses to support the multi-hop pipeline, the hybrid loss and the smoothness loss. GANHopper is a meta-idea. As such, its framework can be easily applied to other direct image-to-image translation methods. There are some future work we would like to explore. First, it would be interesting to develop a multimodal variation of GANHopper. We also believe it's worthwhile to explore variations in our multi-hop pipeline. For instance, we could use different generators for each individual hop. Finally, we would like to investigate the idea that initially spurred the development of GANHopper, generating meaningful extrapolation sequences beyond the boundaries of a given image domain to produce creative and novel outputs. Thank you for watching our presentation. More results and details can be found in the paper.